Welcome back to The Explainer. Today, we are taking a seriously fascinating journey into one of the absolute foundational principles of physics. It's the secret sauce behind our entire modern electrified world, Faraday's law of electromagnetic induction. I mean, if you've ever wondered how the massive power grids of the world actually function, or even just how your induction stove manages to cook your dinner without a flame, you are definitely in the right place. We're going to start things off with some incredibly cool basic physical phenomena, and by the end of this, we'll be peeling back the layers to reveal the deep physics and the math that governs the whole shebang. Okay, let's dive right into this. Here is our quick roadmap for today. We've got 1. The magic of induction. 2. Faraday and Lenz's laws. 3. The math behind the magic. 4. The Faraday paradox. And finally, 5. Real-world applications. I actually want to kick things off by posing a central question to get us all thinking. How exactly do we generate electricity without actually touching any wires together? Back in 1831, a scientist named Michael Faraday discovered that an electric current could be created completely across a gap, just seemingly out of nowhere. Now, it felt like absolute magic at the time, but as you'll see, it's actually an incredibly elegant physical reality that we now call electromagnetic induction. But, to truly grasp this, before we get bogged down in the abstract math and all the equations, we are going to look at a tangible, physical experiment to see this phenomenon happening right before our eyes. Section 1. The magic of induction. If you set up a real physics experiment, like this brilliant schematic from Bit Mesra, it perfectly illustrates this magic in action. We've got this D-shaped aluminum frame that basically acts as a mechanical swing. And right at the bottom of the swing, there's a simple bar magnet. As the frame oscillates back and forth, that magnet rapidly threads its way through a coil of copper wire. Now here's the wild part. Even though the magnet never physically touches the wire, it induces a measurable voltage, an electromotive force, or EMF, right across the ends of the coil. We can actually capture this induced voltage using a basic diode and a capacitor circuit. It's just a beautifully simple setup that proves without a doubt that you can induce an electrical current simply through relative motion. And the data collected from this exact type of experiment reveals a totally direct relationship. If you look at how the recorded amplitude and the time period calculate out, they show the maximum velocity of the magnet as it zips through that coil. When you measure the induced voltage and compare the two, the numbers clearly prove that the induced voltage is directly proportional to the maximum velocity of the magnet passing through the coil. It's pretty straightforward. The faster the magnet moves, the greater the induced electromotive force. Moving on to Section 2, Faraday and Lenz's laws. So we've seen the physical experiment, right? Now let's see how this builds into the actual rulebook that governs what we just witnessed. That brings us to the formal definition of Faraday's law. It states that the magnitude of the induced electromotive force is directly proportional to the rate of change in magnetic flux linkage. So the absolutely crucial phrase here is flux linkage. It isn't just about having a super strong magnetic field. It's about the fact that the flux linked with the coil must change over time to create that electromotive force. Honestly, if you just hold a massive, incredibly strong magnet perfectly still inside a coil, absolutely nothing happens. You need change. But here's the thing. Faraday's law only tells us the magnitude, like the actual size of the voltage. To understand the direction of that induced current, we have to turn to Lenz's law. Lenz's law states that the induced EMF acts in such a direction to produce effects that oppose the change causing it. In the mathematical formula, we represent this with a very important negative sign. You can kind of think of it as the universe pushing back. When you shove a magnet into a coil, the coil generates its own magnetic field that tries to repel the magnet right back out. It's literally nature's way of resisting change. Now, really quickly, before we move on, I want to make sure we intuitively grasp what magnetic flux actually is, because I know it can sound a little abstract. A really great way to visualize magnetic flux is by imagining that our closed loop of wire is filled with a super thin surface, almost like a soap film spanning across a bubble wand. The magnetic flux is simply a measure of how many magnetic field lines are piercing directly through that soap film. And because flux depends on a few different factors, there are actually 3 distinct ways you can change that magnetic flux to induce a current. First off, you can change the magnetic field strength itself, kind of like we did by moving the magnet closer or further away. Second, you can change the area of the coil. So imagine stretching or squishing our soap film loop. And third, you can change the angle of the magnetic field with respect to the loop, like by rotating the coil inside a completely stationary magnetic field. Any of these 3 actions changes the flux, and boom, you have an induced EMF right according to Faraday's law. Section 3, the math behind the magic. Okay, so we've seen the experiments, and we know the rules. Now let's formalize the physical behaviors we've been talking about. Look at how places like Oxford Physics math this out. A wire loop being pulled completely out of a uniform magnetic field with a constant velocity, which we label v. The magnetic field, B, is pointing straight out at us. As the loop gets yanked to the right, the charges inside that vertical wire segment on the left are physically moving through the magnetic field. This physical movement creates a force on those exact charges, which is what drives a current. This is a picture-perfect example of what we call motional EMF. And the math for this? It actually builds up step by step from some very basic physics. Step 1, we start with the Lorentz force, which is just the physical force exerted on a moving charge in a magnetic field. Step 2, we calculate the work done per unit charge by taking a line integral all the way around the circuit, which gives us our EMF. And step 3, when you trace the geometry of that moving wire, you can mathematically equate this exact work to the negative rate of change of the magnetic flux. It is just this clean, incredibly elegant derivation that shows exactly how the physical force on a charge translates straight into Faraday's mathematical law. And we don't even have to get completely bogged down in dense calculus to see it. This all mathematically culminates in a huge way with James Clerk Maxwell. He took Faraday's experimental findings and generalized them into a universal law as part of Maxwell's equations. If you look at the differential form, that's the one with the upside-down triangle, known as the del operator, it tells us something profoundly deep about our universe. It says that any time-varying magnetic field will inherently generate a circulating electric field in space, even if there are absolutely no wires present at all. Section 4, the Faraday paradox. Now, if you're sitting there thinking this all sounds perfectly neat and tidy, well, prepare yourself for the edge cases where these simple rules appear to completely fail. What's often taught in basic physics classes is just the flux rule, the idea that you just look at the flux through a simple, closed, infinitely thin loop of wire. But this simplistic assumption breaks down hard in certain setups. For instance, Faraday himself invented a device called the Faraday disk generator. It's basically a spinning conductive disk sitting in a magnetic field. If you apply the simple flux rule to it, it predicts zero EMF. But in reality, a steady current is generated. This creates a massive paradox. The solution requires us to recognize the big difference between the simplistic flux rule and the universally valid Maxwell-Faraday equation combined with that Lorentz force we talked about earlier. So the crucial point here is how we handle the math when things get a little complicated. The paradox is resolved by understanding that Faraday's law fundamentally relies on the total derivative of the magnetic flux with respect to time, not just the partial derivative. When your circuit, or your integration region, is physically moving or rotating or deforming over time, just like that spinning disk, you have to account for both the changing magnetic field and the changing shape of the circuit itself. When you step back and account for the total derivative, the paradox completely vanishes and the math perfectly predicts reality once again. Section 5, Real-World Applications. Let's step away from the paradoxes and the advanced calculus for a minute and bring this all back down to earth. Because how does Faraday's law actually power our modern world? The answer is literally everywhere. Those big transformers on power lines, they use induction to step voltages up and down so power can travel safely over long distances. Your induction cooker uses a rapidly changing magnetic field to induce swirling currents right inside the metal of your pan, heating it up without a single flame. Electromagnetic flow meters use it to measure fluid velocity inside of pipes. And hey, think about an electric guitar. The metal strings vibrate right over a magnetic pickup, changing the magnetic flux and inducing a tiny current that exactly matches the frequency of the note you played. It literally links that simple BIT Mesra swinging magnet experiment directly to your favorite rock solo. I want to leave you with a final thought to ponder today. Take a second and just look around you. How would modern life look without this singular discovery from 1831? Almost every single electrical generator on the planet, from massive wind turbines all the way down to the alternators inside our cars, relies entirely on pushing a magnet past a coil of wire. Michael Faraday's realization that a changing magnetic field creates electricity quite literally built the modern electrified world we get to live in today. Which really begs the question, what seemingly simple, magical physical phenomena are we currently overlooking today that are going to build the world of tomorrow? Thanks for joining me on this explainer, and keep exploring.